Today I am presenting my implementation of experiment 3, which is based on sampling, aliasing, and reconstruction. I implemented the experiment in Python using Google Colab. Instead of directly starting with the theoretical concepts, I will first explain how implemented the experiment in code, then I will show the results and graphs, and finally I will explain all the theoretical concepts and the observations, right? And document in my reported, which are documented in my reports. Here, first I selected the 50 hertz for my first component and 120 hertz for the second component, the input signals. Here 50, F1 is 50 and F2 is 120. The signal that is used in this experiment is xt equals to sine 2t 2 pi ft plus 0.5 sine 2 pi f2t. Since 120 is my highest frequency, Fmax is 120. Therefore, the rate is 2 multiplied by 120, which gives 240. Now coming to time grid, from here the time grid code starts. Duration is 0.1, and here the plot points. Here this is plot points. Next, I created a high resolution time axis for plotting the original continuous time waveform. I used 5000 points. Here, this is 5000. I have written here. Plot point is 5000. But this is not like physical sampling frequency. This is only used to make the reference waveform smooth when I display it. The actually sampling frequency will be separately defined in afterwards. So plotting resolution and physical sampling rates are kept separated in this implementation. Now coming to the original signal, which is here the equation x is equals to np sine 2 np pi f1t and plus 0.5 cross np sine 2 np pi f2t. Here I generated the actual two-tone signal. The first sine waveform has amplitude 1 and frequency 50 hertz. The second sine wave has amplitude 0.5 and frequency 120 hertz. By adding these two signals, it gives my references continuous time waveform. Now coming up to the next point, there are three cases. Here's sampling rate. The different sampling cases. The first is 300 hertz, which is above the rate, and then comes the 240 hertz, exactly equal the Enquest rate, and the third is 180 hertz, which is again the below the rate. This allows me to compare all the behavior to the same signal under three different sampling conditions. Now here I have took the sampling period. Ts is equals to Ts1 minus Ts0. Yes, which is nothing. w- Here, after obtaining the samples, I reconstructed the signal using sync interpolation. The basic idea is the every sample is multiplied by shifted sync function. All the shifted sync functions are here then added together, and in mathematically the reconstruction is uh, xrt equals to summation of x and sync bracket t minus nts by ts. This gives me a continuous looking reconstructed waveform from the discrete samples. Then here it's come to here the Alice frequency function, which is defined by calculate frequency. Here it is FFS, finding the frequency that appears after sampling. Uh, Here I have also implemented a function to calculate the frequency that will appear after the sampling, which is especially important for the understanding all the three cases said above. And the purpose of this calculation is to compare the theoretical LI's frequency with the frequency actually observed in the FFT spectrum. And coming up to next, I will explain the FFT code. Here x is equals to NP FFT signal. Frequency is equals to NP FFT frequency, where n is equal n comma d is equals to dt. Finally, I calculate the magnitude spectrum using FFT. Here I have calculated the magnitude spectrum by using the FFT. Actually, FFT is the thing which converts the signal from the time domain into the frequency domain, which allows me to see which frequencies are present in the original and reconstructed signal. And now, starting with the graphs, here where the demonstration begins. Here I have took the case one where it is f is equals to 300 hertz. The graph one. First the sampling. Here it is the graph. Here the first sampling frequency is 300 hertz. Since my newest rate is 240 hertz, and here it is 240 hertz, and 300 hertz is above the required rate. Here we can see the original reference waveform. Here are the original. This is the waveforms and the actual sample points. The samples are sufficiently dense, which is here, and in the graph 2, which is sync reconstruction. Here it is sync reconstruction. This is a reconstructed waveform. This is the main waveform, and it is the reconstructed one. And the third is magnitude spectrum, wherein the frequencies again in the two main components is like 50 and 120 hertz. Here it is 120 hertz, and in case 2